The question of how life began on Earth has intrigued humans for millennia. But what if the answer is simpler than we imagine? What if life, not just on Earth but across the cosmos, is the inevitable result of chemical processes that naturally occur under the right conditions? This is one of the most fundamental theories about the origin of life, that life is simply a product of chemistry. At its core, this theory suggests that life didn't require some divine spark or a unique, extraordinary event. Instead, it could have evolved from the same chemical processes that govern the rest of the universe, processes that have happened billions of times in countless environments across space and time. To understand this idea, we need to look back at the origins of life on Earth, which many believe began in the primordial soup, an ocean of organic molecules in the early Earth's oceans. This soup contained everything needed to kickstart life: water, carbon, nitrogen, oxygen, and other basic elements. These elements, when exposed to heat, energy, and electrical charges, could bond and form more complex molecules. The first building blocks of life. Imagine a time billions of years ago when the Earth was young. Its surface was violent, with volcanoes erupting, meteorites crashing, and the air filled with gases like methane, ammonia, and carbon dioxide. The Earth's oceans were likely a chaotic mix of simple compounds, a kind of primordial soup where basic molecules interacted and combined to form more complex substances. In the early 1950s, an experiment by Stanley Miller and Harold Urey tested this very idea. They recreated conditions believed to exist on early Earth by placing water, methane, ammonia, and hydrogen in a sealed container, simulating the conditions of the early Earth's atmosphere. They then introduced electric sparks to simulate lightning. After a week, Miller and Urey found that amino acids, the building blocks of proteins, had formed. This experiment was groundbreaking because it demonstrated that the basic ingredients of life could form under natural, non-biological conditions. Since then, scientists have proposed that life could have started with a similar process, where simple molecules combined to form more complex ones. Over time, these molecules became more and more intricate. Complex organic compounds like proteins, nucleic acids, and lipids formed, setting the stage for the development of the first living organisms. Could this happen elsewhere? Now, here's the exciting part. The same chemical processes that led to the formation of life on Earth could also occur on other planets or moons in our solar system and beyond. The basic elements of life, carbon, nitrogen, hydrogen, oxygen, are all common in the universe. These elements are present in comets, asteroids, and gas clouds in space, and even in the atmospheres of other planets. In fact, scientists have already found amino acids and other organic molecules on comets and in interstellar dust. So, what if life could begin in a similar way elsewhere? Could the same building blocks, when subjected to the right conditions, form complex molecules and eventually give rise to life on other planets? The idea seems plausible, especially when you consider the vastness of the universe, with its billions of stars and planets. The chances that some of these planets have the right chemical environment for life to emerge seem incredibly high. The role of water. One of the key ingredients for life on Earth is water. It's the solvent in which most of life's chemical reactions take place. Water helps organic molecules dissolve, interact, and form more complex structures. For life as we know it to exist, a planet or moon needs to have liquid water on its surface. This is why the search for extraterrestrial life often focuses on planets in the habitable zone around stars. This is the region where conditions are just right for liquid water to exist. For example, Mars and some of the moons of Jupiter and Saturn, such as Europa and Enceladus, are considered prime candidates for the presence of water and possibly life. Europa, in particular, has a subsurface ocean beneath its icy shell, where conditions might be suitable for life to emerge, similar to the early conditions on Earth. The role of energy. For chemical evolution to lead to life, energy is crucial. On Earth, energy in the form of sunlight, lightning, and geothermal heat fueled the complex chemical reactions that led to life. On other planets, energy could come from other sources. For example, stars emit radiation, and some planets and moons may have volcanic activity that could provide enough heat to drive these reactions. Even deep space could provide a source of energy in the form of cosmic rays, which are high-energy particles from distant stars and galaxies. Life could, in theory, emerge anywhere in the universe where the right combination of chemical ingredients and energy sources exist. This means that life may not be restricted to planets similar to Earth but could arise in environments we might consider hostile or extreme. For instance, life might thrive deep in the subsurface oceans of icy moons, or even in the atmospheres of gas giants, where energy from lightning or chemical reactions could fuel the necessary processes. Life's complexity and evolution. If life can emerge from simple chemical processes, it will eventually evolve into more complex forms. On Earth, this process took billions of years, from simple molecules to single-celled organisms and eventually to the vast diversity of life we see today. The theory of evolution by natural selection, first proposed by Charles Darwin, suggests that once life begins, it will evolve in response to its environment. Organisms that are better adapted to their surroundings are more likely to survive and reproduce, passing on their beneficial traits to future generations. This process of chemical evolution could also occur elsewhere. Life might begin as simple, single-celled organisms, but over time, it could evolve into more complex forms as the organisms adapt to their environments. On Earth, life evolved to exploit a wide range of niches, from the deepest ocean trenches to the highest mountains, and it's possible that life on other planets could do the same. The search for life elsewhere. As we look for life elsewhere in the universe, we are searching for environments that could support chemical evolution. We focus on places where water exists, where energy sources are available, and where the right chemical ingredients are present. In the past few decades, our ability to detect exoplanets, planets outside our solar system, has dramatically increased. Thousands of exoplanets have been discovered, many of which are in their stars' habitable zones, raising the possibility that some of them may have conditions suitable for life. One of the most exciting discoveries in this search has been the detection of organic molecules on comets, asteroids, and even on other planets. This suggests that the building blocks of life are widespread throughout the cosmos, not just on Earth. In fact, the discovery of such molecules on Mars has fueled speculation that life may have once existed there, or that it could exist today in the planet's underground waters. Scientists are also studying the icy moons of Jupiter and Saturn, particularly Europa, Ganymede, and Enceladus, which are thought to harbor subsurface oceans. These environments may be perfect for chemical evolution, offering the right conditions for life to develop. In fact, Europa's ocean is believed to have liquid water, warmth from tidal heating, and the necessary chemicals for life, ingredients that could foster the same kind of chemical evolution that took place on Earth. Life on other planets. A matter of time? So, if life can emerge from chemical processes in the right environment, the big question is, how likely is it? Given the vast number of stars and planets in the universe, estimated to be in the trillions, the possibility that life has arisen elsewhere seems almost certain. While we haven't found definitive proof of life beyond Earth yet, the search is ongoing, and with each new discovery, the likelihood of finding life elsewhere increases. In conclusion, life, both on Earth and potentially on other planets, may be the result of chemical evolution, an inevitable process driven by the natural laws of chemistry and physics. The ingredients for life are out there, scattered throughout the cosmos. The question is not whether life exists elsewhere, but rather where and when we will find it. As we continue to explore the universe, the possibility of discovering life beyond our planet becomes ever more tantalizing, and each discovery brings us closer to answering one of the most profound questions humanity has ever asked. Are we alone in the universe? When we talk about the origins of life, we usually assume that life began right here on Earth. But what if life didn't start on Earth at all? What if life was brought here from somewhere else in the cosmos? This is the essence of the Panspermia Hypothesis, a fascinating and somewhat radical idea that suggests life could have originated elsewhere in the universe and been transported to Earth or other planets via comets, asteroids, or even interstellar dust. The theory of panspermia isn't new. It has roots in ancient history. The Greek philosopher Anaxagoras proposed a similar idea as far back as the 5th century BCE, suggesting that life might have come from the stars. But it was in the 20th century that the idea gained significant scientific attention, primarily through the work of scientists like Fred Hoyle and Chandra Wickramasinghe, who argued that life could survive the harsh conditions of space and be carried across the universe. How would life travel through space? To understand how panspermia could work, we need to consider how life could survive the journey through space. Space is an incredibly hostile environment. Temperatures can reach hundreds of degrees below freezing, and radiation from the sun and cosmic rays can be lethal. However, it's possible that microorganisms or even more complex forms of life could survive in space for extended periods. Microbes known as extremophiles, organisms that thrive in extreme environments like deep-sea vents, hot springs, or even the frozen tundra, provide important evidence for this idea. Some extremophiles can survive harsh conditions that would kill most life on Earth. For example, certain bacteria can survive exposure to extreme radiation, vacuum, and freezing temperatures. In fact, in 2005, scientists sent bacteria into space aboard a European Space Agency mission and found that some of them were still viable after being exposed to space for 18 months. The key to the survival of these organisms is their ability to form spores, dormant, highly resistant forms of life that can withstand environmental stress. These spores could potentially survive a journey through space, protected by the rocky surface of a comet or asteroid. Comets, asteroids, and the transfer of life. So, how would life actually get from one planet or moon to another? The most likely method is through the impact of space debris. When a comet or asteroid collides with a planet or moon, it releases a massive amount of energy. If the impact is powerful enough, it can eject material from the planet's surface into space, where it could eventually land on another planet or moon. This process is called planetary ejection. It has been suggested that such impacts could send chunks of Earth, or even other planets, flying through space, carrying with them bacteria or other microorganisms. These bits of rock, containing life, could travel across the solar system, or even to other star systems, where they might eventually land on a suitable planet, potentially seeding life there. In fact, it's possible that the Earth itself was seeded with life from elsewhere. According to the Panspermia Hypothesis, our planet might have received its first microbes from a comet or asteroid that collided with a distant world in another part of the universe. This could have set the stage for the chemical evolution that led to life on Earth. Evidence supporting panspermia. While the idea of panspermia might seem far-fetched, there's some intriguing evidence that supports it. For example, organic molecules have been found on comets, asteroids, and even on the surface of Mars. These molecules, like amino acids, are the building blocks of life, and their presence in space suggests that the raw ingredients for life are abundant throughout the universe. One of the most striking pieces of evidence comes from the analysis of a Martian meteorite known as ALH 84001, which was found in Antarctica in 1984. Scientists discovered microscopic structures in the meteorite that resembled fossilized bacteria. While there is still debate about whether these structures are indeed evidence of life, their discovery sparked significant interest in the possibility that life could have traveled to Earth from Mars, or that Mars could have been the source of life on Earth. Moreover, in 2019, researchers detected organic molecules on the surface of Comet 67P/Churyumov-Gerasimenko, the target of the European Space Agency's Rosetta mission. The discovery of complex organic molecules, including amino acids, provided more evidence that the building blocks of life could be widespread throughout the cosmos, not just confined to Earth. Could panspermia explain life's uniqueness? One of the most intriguing aspects of the Panspermia hypothesis is the question of whether life on Earth is uniquely Earth-like or if it follows a universal blueprint. If life is the result of panspermia, it raises the possibility that life on other planets could be quite similar to life on Earth, since it would have originated from the same cosmic sources. On the other hand, panspermia could also suggest that life in the universe is more diverse than we can imagine. Life could exist in forms that are radically different from what we know, adapted to the conditions of their home planets. For instance, life might thrive in environments that are completely hostile to Earth-based organisms, such as the sulfuric acid clouds of Venus or the methane lakes of Titan, Saturn's moon. The discovery of such life would redefine our understanding of what is possible in the universe. But there's another twist to this. What if life on Earth wasn't the result of a simple cosmic accident, but part of a larger cosmic pattern? The Panspermia hypothesis raises profound philosophical questions about the origins of life. Could life itself be a widespread, natural phenomenon that occurs in many places in the universe, or is Earth uniquely suited to harbor life? Could we one day discover that life is so common in the universe that it's simply waiting to be found, just beyond the reach of our telescopes? Mars and the search for panspermia evidence. One of the most exciting places to search for evidence of panspermia is Mars. For years, scientists have been fascinated by the idea that Mars might have once hosted life. The planet has evidence of ancient riverbeds, lake beds, and even oceans, suggesting that it once had liquid water on its surface. Today, Mars is cold and dry, but it's still considered one of the best candidates for finding signs of past life. If life did exist on Mars in the distant past, it's possible that it was wiped out by a cataclysmic event, such as a massive asteroid impact or the planet's loss of its atmosphere. However, some scientists believe that if life ever existed on Mars, it could have traveled to Earth via meteorite impacts. Evidence for this theory could be hidden in the ancient rock layers of Mars, or perhaps even in the meteorites that occasionally fall to Earth from the red planet. NASA's Perseverance rover, currently exploring the surface of Mars, is specifically tasked with searching for signs of ancient life. If microbial life was once present on Mars, finding these signs could strengthen the case for panspermia, suggesting that life from Mars could have been transported to Earth. Is panspermia the only answer? While the idea of panspermia is compelling, it's not the only explanation for life's origins. Some scientists still believe that life arose independently on Earth through a process of chemical evolution, as we discussed in the previous section. Others suggest that life could have originated in Earth's deep oceans, where the right combination of chemicals and conditions allowed life to emerge naturally. However, what makes the idea of panspermia so interesting is that it provides a broader perspective on the origins of life. It suggests that life could be a cosmic phenomenon, spreading from planet to planet, carried on the wings of comets and asteroids, drifting through space on a journey that spans millions of years. Life beyond Earth. The search continues. As we continue to search for life beyond Earth, the Panspermia hypothesis reminds us that the universe is vast, and the possibilities are endless. If life can travel across the cosmos, then there may be a whole network of living planets out there, waiting to be discovered. Whether life is common or rare, the search for extraterrestrial life continues to be one of the most exciting and important scientific endeavors of our time. In the next section, we'll dive into another fascinating possibility: life in extreme environments, such as the subsurface oceans of moons like Europa and Enceladus. Could life exist in these places, where the conditions seem too harsh for life as we know it? Stay tuned, because the mysteries of life's origins are just beginning to unfold. The Earth, as we know it, is a unique haven for life, with its comfortable atmosphere, stable temperatures, and abundant resources. However, what if life doesn't always need the familiar conditions we associate with habitability? What if life can thrive in environments that are incredibly extreme, places that we might assume would be inhospitable? In this section, We'll explore some of the most extreme environments in our own solar system and investigate the possibility that life could exist in places that seem totally unlivable by Earth's standards. One of the most exciting areas of scientific exploration revolves around the subsurface oceans of moons and planets in our solar system, particularly the moons of Jupiter and Saturn, such as Europa, Enceladus, and Ganymede. These moons are ice-covered and have been thought to harbor liquid water beneath their frozen surfaces, potentially providing the conditions needed for life to exist. Could life survive there? And if it does, what might it look like? Europa, the ice-covered ocean. Let's begin with Europa, one of Jupiter's moons, which has become a focal point in the search for extraterrestrial life. Europa is covered in a thick shell of ice, but beneath this ice, scientists believe there exists a vast ocean of liquid water, kept warm by tidal heating, the process by which gravitational forces from Jupiter and its other moons create friction, generating enough heat to maintain a liquid state. The discovery of Europa's ocean came about through detailed observations from spacecraft like NASA's Galileo, which revealed the moon's icy surface is cracked and fractured, suggesting the presence of an active, liquid subsurface. Europa is about 90% covered in ice, and beneath this ice shell, the ocean is thought to be in contact with a rocky ocean floor, creating the possibility of hydrothermal vents, similar to those found on Earth's ocean floor, where life thrives in the absence of sunlight. On Earth, these hydrothermal vents are teeming with life, organisms that don't rely on sunlight for energy, but instead depend on the chemicals in the Earth's crust. These life forms, known as chemosynthetic organisms, draw energy from minerals and gases such as hydrogen sulfide and methane, and they form the base of a thriving ecosystem that can exist without any light. This discovery challenges the long-held belief that life can only exist in the presence of sunlight and demonstrates how adaptable life can be, even in the harshest of environments. Enceladus, a moon full of secrets. Another fascinating world in our solar system is Enceladus, one of Saturn's moons. Enceladus is only about 500 kilometers in diameter, making it a relatively small moon, but it has some of the most compelling evidence for the potential existence of life beyond Earth. In 2005, NASA's Cassini spacecraft made a remarkable discovery. Plumes of water vapor, ice particles, and organic compounds were erupting from Enceladus' southern pole. These geysers spout material from a liquid ocean beneath the moon's icy shell, creating what scientists call a cryovolcanic environment. Volcanic activity driven by water and ice instead of lava. The fact that Enceladus' subsurface ocean is interacting with the moon's surface is highly significant. These plumes have been analyzed and found to contain organic molecules, such as amino acids, which are the building blocks of life. The presence of these organic molecules, combined with the fact that the subsurface ocean of Enceladus is in contact with the moon's rocky core, raises the exciting possibility that life could be living there, just as it does in Earth's deep ocean vents, where similar conditions exist. These compounds don't prove the existence of life, but they strongly suggest that the fundamental ingredients for life exist on Enceladus. The Cassini mission's findings, along with the ongoing research into Enceladus plumes, continue to spark interest in the idea that life may be able to survive in even the most extreme environments, such as a dark, frozen moon. Far from the warmth of the sun, scientists are eagerly awaiting the next phase of exploration, with planned missions like NASA's Europa Clipper and potential landers to Enceladus, hoping to answer the question, can life exist in these frozen ocean worlds? Titan, methane lakes, and a dense atmosphere. Beyond the icy moons of Europa and Enceladus, there is another fascinating candidate in the search for life. Saturn's moon Titan. Titan is an enigma. It is the second largest moon in the solar system and has a thick atmosphere, something that many other moons and planets lack. Titan's atmosphere is primarily composed of nitrogen, with methane and hydrogen present in significant quantities, which creates a dense, hazy environment unlike anything we experience on Earth. While Titan may seem inhospitable at first glance due to its frigid temperatures, which hover around -290 degrees Fahrenheit, -179 degrees Celsius. The moon has intrigued scientists because it features vast lakes and seas made of liquid methane and ethane, two hydrocarbons that are gases at Earth's temperatures but exist as liquids in the extreme cold of Titan. These lakes are the largest known bodies of liquid on any planetary body outside Earth, and they create a landscape that is eerily similar to the surface of Earth, albeit with radically different chemicals at play. Could life survive in Titan's methane lakes? This might sound strange, but scientists are exploring the possibility that life on Titan could be based on methane and ethane instead of water. Methane is a highly reactive compound, and while it doesn't have the same properties as water, it could still provide a solvent for life, albeit a different kind of life from what we're familiar with. In fact, some researchers have even speculated that instead of relying on water, life on Titan could use liquid methane as a solvent for chemical reactions. This would create a completely alien form of life, very different from anything we could imagine, but still potentially life as we understand it in the broadest sense. Titan's atmosphere also contains complex organic molecules, such as cyanoacetylene and acrylonitrile, which could form the building blocks of life. While these molecules don't prove that life exists on Titan, they suggest that the moon could be a prime location to search for signs of life, especially if future missions are able to explore the surface and atmosphere in more detail. The limits of life. Can life survive without water? As we examine these extreme environments, we begin to ask, can life exist without water? While Earth is the only known place where life exists with the abundance of liquid water we're familiar with, these findings on Europa, Enceladus, and Titan challenge the notion that water is absolutely essential for life. Perhaps it is the chemistry and energy that are more important than the solvent itself. After all, if life can exist in the hydrothermal vents of the deep ocean, in the frozen tundra, and even in acidic hot springs, there's no reason why it couldn't adapt to radically different environments on other worlds. On the other hand, it's important to recognize that life as we know it is shaped by specific environmental conditions, especially those that involve liquid water. While there may be forms of life that thrive in completely foreign environments, the search for life continues to focus on finding places that resemble Earth's oceans, where the ingredients for life can interact in familiar ways. The future of extreme environments exploration. The search for life in extreme environments is one of the most exciting frontiers in planetary science. As our technology advances, the possibilities for exploration expand, and our understanding of what makes a planet or moon habitable continues to evolve. While we don't yet have definitive proof that life exists on Europa, Enceladus, or Titan, each new discovery brings us closer to answering that tantalizing question. Are we alone in the universe? Future missions like NASA's Europa Clipper, which will conduct detailed reconnaissance of Europa's subsurface ocean, and Dragonfly, a rotorcraft that will explore Titan's surface, will provide more insight into the potential for life in these far-flung, icy worlds. With the advancements in technology and our growing understanding of extremophiles on Earth, the possibility that life exists in places we've never imagined is becoming more and more plausible. As we delve deeper into the possibilities of life elsewhere in the universe, one of the most exciting ideas is that life might not necessarily rely on water as we know it. On Earth, all known life forms depend on liquid water for chemical reactions, metabolism, and energy transfer. However, what if there are alternative solvents other than water that could support life in different environments? To understand this possibility, we need to explore how life could potentially use other liquids as solvents, and how these environments might be radically different from Earth's watery ecosystems. In this section, we will examine how life could exist in solvents like methane, ammonia, or even hydrogen, and what such life might look like. The nature of water and its unique qualities. Before we jump into the possibility of alternative solvents, it's important to understand why water is so crucial to life as we know it. Water is often referred to as the universal solvent because it can dissolve a wide variety of substances, facilitating the complex chemical reactions that sustain life. Water has several unique qualities that make it ideal for supporting life. High heat capacity. Water can absorb a large amount of heat without significantly changing temperature, which helps stabilize environmental conditions on Earth. Polarity. The polar nature of water molecules allows it to dissolve many ionic and polar compounds, facilitating a variety of chemical reactions that are essential for life processes. Liquid state at life-supporting temperatures. Water remains in a liquid state within a wide temperature range, between 0 degrees Celsius and 100 degrees Celsius, 32 degrees Fahrenheit to 212 degrees Fahrenheit, making it stable in many environments. But what if life could exist in an environment where liquid water isn't present, and instead, another solvent like methane, ammonia, or even ethylene glycol could serve the same purpose? Methane and ethane, a liquid hydrocarbon world. One of the most intriguing alternatives to water as a solvent for life is methane, CH4, and its cousin ethane, C2H6. These compounds are hydrocarbons, molecules made up of carbon and hydrogen, and are both gases on Earth under normal conditions. However, under the extremely cold temperatures of Titan, Saturn's largest moon, methane and ethane are liquid, and they cover the surface in vast seas and lakes. In 2004, the Cassini spacecraft revealed the first direct evidence of lakes and seas on Titan's surface, primarily made of liquid methane and ethane. The surface temperature on Titan hovers around -290 degrees Fahrenheit, -179 degrees Celsius. So liquid methane exists in stable pools, providing a fascinating environment for life to potentially take root. Could life exist in liquid methane? It sounds strange, but some scientists have proposed that life could potentially adapt to methane as a solvent. The chemical processes that support life on Earth, such as metabolism, rely on solvents that can move molecules around and facilitate chemical reactions. On Titan, the processes would have to work at extremely low temperatures, and the reactions would have to occur much more slowly than those on Earth. However, life that depends on methane would have to be adapted to survive under cold, low-energy conditions. In a methane-based ecosystem, chemistry would look very different from Earth's water-based biochemistry. For example, instead of relying on carbon-based molecules like proteins and DNA to carry out the work of life, methane-based life might use silicon, which is chemically similar to carbon but can form longer, more stable chains in non-aqueous environments. Some scientists speculate that life on Titan might use methane or ethane for respiration and energy production, essentially breathing in a completely alien way compared to Earth's oxygen-based organisms. Ammonia, another alternative solvent? Another possible alternative to water is ammonia, NH3, which is chemically similar to water in some ways. Ammonia, in its liquid form, can dissolve many of the same compounds as water, allowing it to serve as a solvent for life. The key difference between water and ammonia is that ammonia has a lower boiling point than water, meaning it would remain liquid in environments that are much colder than Earth's. Ammonia is abundant in the universe, and it has been detected in the atmospheres of many moons, planets, and even interstellar clouds. The surface of Neptune's moon Triton, for instance, is believed to be rich in ammonia. On Earth, we know that ammonia supports life in certain microbial ecosystems, and in laboratory conditions, scientists have successfully grown small organisms in ammonia solutions. Ammonia has some advantages over water as a solvent. For example, ammonia has a wider range of chemical reactions that can occur at lower temperatures, which could be useful for life in colder environments, such as those found on distant moons or planets. However, ammonia is also more toxic than water to many Earth-based organisms, so life in an ammonia-based world would likely have to be vastly different from anything we're familiar with. Could life exist in ammonia lakes or oceans, like those that might exist on moons such as Titan or Triton? Some researchers believe that ammonia might be able to support simple life forms, though the specifics of how such life could function remain largely theoretical. Still, the idea that life might use ammonia instead of water opens the door to new possibilities for life on planets or moons that are far colder than Earth. Hydrogen, the simplest possible solvent. One of the most speculative ideas regarding alternative solvents for life revolves around hydrogen, the simplest and most abundant element in the universe. Hydrogen in its liquid form can exist under extremely low temperatures, and it has been suggested that life could potentially use hydrogen as a solvent in environments where the temperature is low enough for hydrogen to remain liquid. Life based on hydrogen would require a radically different chemistry than anything on Earth. Instead of using carbon-based molecules to carry out the necessary functions of life, hydrogen-based life would likely require entirely new types of biochemistry, possibly relying on hydrogen bonding as its mechanism for forming stable, complex structures. The challenges of such a system would be immense, but in a hydrogen-rich environment, perhaps on the surface of a gas giant like Jupiter or Saturn, such an exotic form of life might be able to exist. Hydrogen-based life forms would also have to rely on extremely low-energy chemical reactions, likely using hydrogen as both a fuel source and a solvent. The main difficulty with such a life form is that hydrogen, being a very light and reactive element, would have trouble forming the complex molecules needed for life in the way that carbon and water can on Earth. The search for life beyond water. Implications for the universe. The exploration of alternative solvents raises an important and philosophical question. What does life need to thrive? Earth's biochemistry is built around water, and life on Earth is tightly adapted to its properties. However, the growing interest in life beyond Earth suggests that life might not be bound by the same constraints we assume. If life can survive in methane lakes on Titan, or ammonia oceans on Triton, or even in environments where hydrogen is the primary solvent, it dramatically expands the scope of where we might find life. Scientists are now actively searching for environments beyond Earth where such non-water-based life could exist. Planets orbiting other stars, so-called exoplanets, may harbor life forms that have evolved in ways we can't even imagine. The habitable zone, the distance from a star where liquid water can exist on the surface of a planet, remains a key focus of the search for life. But the discovery of alternative solvents challenges the notion that planets outside the habitable zone are automatically inhospitable. Life, it seems, is far more adaptable and resourceful than we have given it credit for. As we continue to explore the universe, the question of whether water is necessary for life may become less important than the realization that the potential for life in the cosmos is far more diverse than we ever expected. In the search for life beyond Earth, one of the most fascinating theories is panspermia, the idea that life on Earth may have originated from microorganisms or chemical compounds that were transported here from space. This theory challenges the traditional view that life arose independently on Earth, suggesting that life could exist, or even be distributed, across the cosmos. Could life be seeded across the universe by meteoroids, comets, or other celestial bodies, possibly via interstellar travel? If so, could the materials necessary for life be common throughout the universe, waiting for the right conditions to spark the development of life? Let's explore how panspermia might work and its potential implications for our understanding of life's origins. The basics of panspermia, a cosmic seed. The word panspermia comes from the Greek words pan, meaning all, and sperma, meaning seed. Essentially, panspermia suggests that life, or the building blocks of life, could be widespread throughout the universe, and life on Earth could have originated from these seeds. While this doesn't imply that humans or complex life came from space, it does suggest that the basic ingredients for life, such as amino acids, might be carried on cosmic dust or meteorites, traveling across the vast distances between stars. The theory has existed for centuries, but in recent decades, scientific developments have given it more credence. Researchers have found organic molecules, such as amino acids, nucleobases, the building blocks of DNA and RNA, and other vital compounds, on comets, asteroids, and interstellar dust. These molecules could have been formed in the early solar system, and over time they might have found their way to Earth via impacts. However, panspermia is not just about the delivery of life's building blocks. It suggests that life itself could travel across space, potentially surviving in harsh conditions. While early concepts of panspermia were more speculative, modern science is now examining how life, or its essential components, could survive in space, where conditions are extreme. Evidence of organic molecules in space. A key line of evidence supporting the idea of panspermia is the discovery of organic molecules in space. Organic molecules are carbon-based compounds that form the backbone of life as we know it. These molecules are the basic ingredients of life, and their presence in space suggests that the fundamental components necessary for life are not unique to Earth. The comet Wild 2, visited by NASA's Stardust mission in 2004, provided a wealth of information about the organic compounds present in comets. Stardust captured samples of dust and gas from the comet, and when scientists analyzed the material, they found amino acids, simple organic molecules that are the building blocks of proteins. These findings were significant because they showed that organic compounds, which are key to the development of life, are widespread in our solar system. Additionally, interstellar dust grains, tiny particles that exist in the space between stars, have been found to contain complex organic molecules. The Rosetta mission, which investigated the comet 67P/Churyumov-Gerasimenko, provided further evidence that comets might play a role in delivering organic compounds to planets. These findings suggest that the ingredients for life are abundant in space, possibly giving rise to life on planets and moons that encounter these compounds. Can life survive space travel? While the discovery of organic molecules is compelling, the real challenge for the panspermia theory is whether actual life, microorganisms, or even primitive cells could survive the harsh conditions of space. After all, space is an incredibly hostile environment, with extreme radiation, freezing temperatures, and a near-complete vacuum. Could life survive in such an environment long enough to travel from one celestial body to another? Several studies suggest that certain extremophiles, organisms that thrive in extreme conditions, might have the ability to survive in space. Some of the most resilient microorganisms on Earth, such as tardigrades, also known as water bears, have been shown to endure the vacuum and radiation of space. In 2007, scientists sent tardigrades into space aboard the European Space Agency's Photon M3 mission, and many survived exposure to the harsh conditions of space. These findings suggest that microorganisms could potentially survive the journey through space, even for extended periods. Other microorganisms, such as bacteria and fungi, have also been shown to survive in space-like conditions. Certain bacteria are known to form spores, which are highly resistant to radiation, temperature extremes, and dehydration. These spores could potentially be carried on meteoroids or other debris, traveling across vast distances through space until they encounter a hospitable environment. Moreover, certain meteorites, such as the Murchison meteorite that fell in Australia in 1969, have been found to contain organic compounds and amino acids, suggesting that life, or the building blocks of life, may have been transported across the solar system by these objects. The mechanism of panspermia, how life could travel. One of the key questions of the Panspermia hypothesis is how life, or its basic components, could travel from one planet to another. It is believed that life could be transferred in a number of ways. Impact events. When an asteroid or comet collides with a planet, it can eject material into space. If microorganisms or organic compounds are embedded in the impact site, they could be propelled off the planet and carried to other worlds. This process, known as lithopanspermia, is believed to be one of the most likely methods by which life might spread across the solar system or even between stars. Ejected material. Once a celestial body is impacted by a large enough asteroid, the force of the collision can send fragments of rock, ice, and dust into space. These fragments can travel across vast distances, potentially carrying microorganisms on their surface. Over millions or even billions of years, these fragments could collide with other planets, delivering life or its building blocks. Solar wind and cosmic radiation. Another potential mechanism for the spread of life is the solar wind, a stream of charged particles emitted by the sun. These particles could carry small fragments of microbial life on their way through the solar system. Similarly, cosmic radiation could carry particles on a journey through space, facilitating the spread of life across great distances. Implications of panspermia. What does it mean for life elsewhere? If panspermia is correct, it suggests that life may be far more widespread than we think. Instead of life arising independently on every suitable planet, it could be that life or its essential components were seeded across the universe. This could mean that life could exist on countless worlds, but that the forms of life we encounter might be radically different from what we are familiar with on Earth. If life on Earth originated from space, it would also raise the question of where that life originated. Did life itself begin in the depths of space, possibly on an ancient planet or moon? Or was it the result of a cosmic collision, in which life from another part of the universe arrived on Earth billions of years ago? This concept expands the idea of life's origins from being a local phenomenon to a cosmic one. Moreover, the theory of panspermia introduces the idea that life might not be restricted to Earth-like planets within the habitable zone. Planets and moons with extreme environments, such as Europa's icy oceans, Mars' ancient surface, or even the methane lakes of Titan, could harbor life that evolved in ways we cannot yet imagine. Panspermia also has profound implications for the search for extraterrestrial life. Instead of just looking for planets with liquid water, we may need to consider planets that have been in contact with material from other parts of the universe. The presence of organic molecules, chemicals essential for life, or even evidence of ancient impacts on other planets could provide clues that life may exist or have once existed elsewhere. The search for life beyond Earth, a new frontier. The idea of panspermia encourages scientists to broaden their search for life. Missions such as NASA's Perseverance rover on Mars or the James Webb Space Telescope, JWST, focus not only on the possibility of life existing on other planets and moons, but also on understanding how life might have traveled across space, and whether the ingredients of life can be found on other worlds. As we continue to study the cosmos, the theory of panspermia reminds us that the story of life might not be confined to our planet alone. The more we learn about life's potential to survive in extreme conditions and travel across space, the more likely it seems that life, in one form or another, is out there waiting to be discovered. As we continue to explore the potential for life beyond Earth, one of the most fundamental concepts guiding our search is the habitable zone. Often referred to as the Goldilocks zone, this region around a star is the perfect distance where conditions are neither too hot nor too cold for liquid water to exist on the surface of a planet. Given that water is crucial for life as we understand it, the search for planets within the habitable zone of their stars has become a major focus of astrobiology and space exploration. But does the existence of a planet in the habitable zone guarantee that life can form and thrive? How precise must the conditions be for life to emerge? And what if the definition of the habitable zone needs to be expanded to accommodate forms of life that don't depend on water? In this section, we'll explore the intricacies of the habitable zone and consider how our understanding of it may evolve as we learn more about the universe and the diverse ways in which life might exist. What is the habitable zone? The habitable zone is a concept that came into prominence with the discovery of exoplanets, planets orbiting stars outside our solar system. It refers to the region around a star where temperatures are suitable for liquid water to exist on the surface of a planet. Water is a key ingredient for life on Earth, so it is often assumed that planets within the habitable zone might be capable of supporting life. To understand why this zone is so crucial, we need to consider a few key factors. Temperature. The temperature of a planet is determined by the balance between the amount of energy it receives from its star and the amount of heat it radiates back into space. If a planet is too close to its star, it will be too hot for water to remain liquid, leading to a runaway greenhouse effect like on Venus. If it is too far from its star, the surface temperature will be too cold for liquid water to exist, resulting in a frozen world, like Mars or the outer moons of the solar system. Atmosphere. A planet within the habitable zone may have the right conditions for liquid water, but it also needs a stable atmosphere. The atmosphere helps regulate the planet's surface temperature by trapping heat and preventing extreme fluctuations. Without a thick atmosphere, a planet might not be able to retain the warmth necessary to support liquid water. Star type. The type of star that a planet orbits also plays a crucial role in defining the habitable zone. Stars like the Sun, which are classified as G-type main sequence stars, have a habitable zone that is relatively broad. However, smaller stars like red dwarfs have a much narrower habitable zone. These stars are also more prone to stellar flares, which could make conditions less stable for life. The search for exoplanets in the habitable zone. With the advent of telescopes like the Kepler Space Telescope and the James Webb Space Telescope, astronomers have been able to identify thousands of exoplanets, many of which reside in the habitable zones of their stars. In fact, the discovery of Earth-like planets in habitable zones has become one of the most exciting areas of research in astrobiology. For example, one of the most notable discoveries is the exoplanet Kepler 452b, often referred to as Earth's cousin. This planet orbits a star similar to the Sun, and it is located in the habitable zone of its star, at a distance that suggests it could have surface conditions conducive to liquid water. While we don't yet know if Kepler 452b harbors life, its discovery has sparked much excitement about the potential for Earth-like planets in the galaxy. Other exoplanets, like Proxima Centauri b, orbiting the closest star to our Sun, Proxima Centauri, also fall within the habitable zone, and future missions are planned to study them in more detail. The TRAPPIST-1 system, with its 7 Earth-sized planets, is another key focus of exploration. 3 of these planets are in the star's habitable zone, and scientists are keen to learn whether they might host life. The discovery of exoplanets in the habitable zone raises an important question. What defines the right conditions for life to form and thrive? If a planet is in the habitable zone, it doesn't guarantee life, but it might make it more likely. But what about planets that exist outside this zone? Could life thrive there too? Expanding the habitable zone. Can life exist in extreme environments? One of the most significant challenges to the traditional understanding of the habitable zone is the realization that life on Earth can survive in places that are far more extreme than what we would consider habitable. In fact, extremophiles, organisms that live in extreme environments, are found in some of the harshest conditions on Earth. For example, life has been found in subglacial lakes in Antarctica, where temperatures are well below freezing. Other extremophiles survive in acidic hot springs, deep-sea hydrothermal vents, and even highly radioactive environments. These organisms have evolved to thrive in conditions that would be deadly to most other forms of life, suggesting that life can exist in environments that are far more extreme than what we see in the traditional habitable zone. This has led scientists to reconsider the concept of the habitable zone. Instead of focusing solely on planets with liquid water and moderate temperatures, researchers are beginning to explore the potential for life in environments with extreme conditions. For example, moons like Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, have subsurface oceans beneath their icy crusts, and these oceans could potentially harbor microbial life, even though the surface temperatures on these moons are far too cold to support life as we know it. Could life exist on Venus, despite its scorching surface temperature and toxic atmosphere? In recent years, scientists have proposed that Venus might harbor life in its upper atmosphere, where conditions are much more temperate. The discovery of phosphine, a gas associated with biological processes, on Venus sparked a renewed interest in the possibility of life there, even though its surface is inhospitable. Similarly, on Mars, evidence of ancient water in the form of riverbeds and lakes suggests that the red planet may have been habitable in the past. Today, while liquid water no longer exists on the surface, Scientists are still exploring the potential for microbial life in Mars' subsurface, or within salty brines that may exist beneath the surface. The implications of life in the extended habitable zone. The growing recognition that life might exist beyond the traditional habitable zone has profound implications for the search for extraterrestrial life. If life can survive in extreme environments, then we need to broaden our search to include planets, moons, and other celestial bodies that may not fall within the classical habitable zone but still offer the potential for life to flourish. The extended habitable zone could include environments where water is present in a form other than liquid, such as water vapor or ice, or where energy is provided not by a star but by geothermal activity or other heat sources. Titan, Saturn's largest moon, for instance, has lakes and rivers of liquid methane, and it is one of the most intriguing places for astrobiologists to explore. Though its chemistry is very different from Earth's, Titan could still provide insights into how life might arise in an environment vastly different from our own. How do we study planets outside the habitable zone? To search for life in the extended habitable zone, astronomers use a variety of tools and techniques. One of the most effective methods is the transit method, which detects the slight dimming of a star as a planet passes in front of it. This method has been responsible for many of the exoplanet discoveries made by telescopes like Kepler and TESS, transiting exoplanet survey satellite. Another promising approach is the study of biosignatures, chemicals that indicate the presence of life. For example, the James Webb Space Telescope, JWST, will be able to analyze the atmospheres of exoplanets, looking for gases like oxygen, methane, and carbon dioxide, which could suggest biological activity. Despite all these advances, the search for life remains challenging. While scientists are learning more about where to look, they are also becoming more open to the idea that life might not need the same conditions that Earth has to thrive. Life is resilient and adaptable, and the universe may offer countless environments where life can take root. When we think of life, we often imagine carbon-based organisms relying on water as a solvent for their biochemical reactions. This vision is based on the life forms we know best, those on Earth. However, as we expand our search for life beyond our planet, scientists are exploring the intriguing possibility that life elsewhere in the universe might not adhere to the same rules we are familiar with. What if life does not rely on carbon or water? Could there be alternative biochemistries that support life in forms we cannot even begin to comprehend? In this section, we will explore how the search for extraterrestrial life might change if life can exist in completely alien forms, using different chemical building blocks. Could life thrive using silicon, ammonia, or even methane instead of water? And what does this mean for our understanding of life itself? The carbon-water life paradigm, why it works on Earth. Before we delve into alternative biochemistries, let's understand why life on Earth relies so heavily on carbon and water. Carbon is uniquely suited to form the complex molecules required for life. It can bond with a variety of other elements, forming chains, rings, and structures that make up the macromolecules like proteins, nucleic acids, DNA and RNA, and lipids. These molecules are essential for the processes that sustain life. Water is an equally crucial component for life on Earth. It acts as a solvent, facilitating chemical reactions by dissolving many substances. Water's polar nature, with one side being slightly positive and the other negative, allows it to dissolve a wide range of compounds, making it a perfect medium for the biochemical reactions that support life. Additionally, water has a high heat capacity, meaning it can absorb and release heat without drastically changing temperature, helping to stabilize the conditions for life on Earth. However, while carbon and water form the backbone of life as we know it, we cannot assume that life elsewhere in the universe would follow the same blueprint. The universe is vast, and the conditions on other planets and moons might be radically different from those on Earth. Silicon-based life, a carbon alternative? One of the most popular hypotheses for alternative life chemistries is silicon-based life. Silicon, like carbon, is a group 14 element on the periodic table and shares some chemical similarities. It can form long chains and complex molecules, much like carbon, which is why scientists have long speculated that silicon could serve as a potential backbone for life elsewhere in the universe. However, silicon does not bond as easily as carbon. Silicon-silicon bonds are generally weaker than carbon-carbon bonds, and silicon compounds tend to be less flexible and more brittle than their carbon counterparts. Additionally, silicon-based compounds like silicon dioxide, the equivalent of carbon dioxide, are solid at room temperature, whereas carbon dioxide is a gas. This makes it harder for silicon to function as efficiently in a living organism's biochemical processes as carbon does. Still, the idea of silicon life is intriguing, especially in environments where carbon might be less abundant or where conditions are too extreme for carbon-based life to survive. For example, on a planet with extremely high temperatures, silicon might form more stable molecules than carbon. Silicon-based life might exist in environments where the chemistry of Earth's biochemistry cannot function. Imagine a world with intense volcanic activity or extreme heat. Here, silicon-based organisms might thrive, using different mechanisms to sustain life. Ammonia, the liquid that could replace water. Another fascinating alternative to water as the solvent for life is ammonia, NH3. On Earth, water is the universal solvent that enables the chemical reactions needed for life. But on colder planets or moons, water might freeze, making it unusable as a solvent. Ammonia, however, is a liquid at much lower temperatures, and it could potentially serve as a solvent for life in environments where water would be frozen solid. Ammonia is chemically similar to water in some ways. It is also polar, which means it can dissolve a variety of substances, and it has a relatively high heat capacity. However, ammonia also has significant differences from water. It is more toxic to Earth-based life forms, and it has a much narrower temperature range where it remains liquid. The lower temperature threshold for ammonia makes it potentially suitable for life in colder environments, such as moons orbiting gas giants like Saturn or Jupiter. Titan, Saturn's largest moon, is one such place where ammonia might play a role in supporting life. Titan has lakes of liquid methane and ethane on its surface, and although methane is not considered a good solvent for life, ammonia might be found in its atmosphere or subsurface. Scientists are speculating that ammonia-based life might be able to adapt to Titan's cold environment, using ammonia as a solvent instead of water. The search for life on Titan might therefore expand to include organisms that don't need liquid water at all. Methane, the liquid of possibility. While water, ammonia, and silicon are the most commonly discussed alternatives to carbon and water, methane is also considered a potential solvent for life. Methane, CH4, is a simple molecule composed of carbon and hydrogen, and it remains liquid at very low temperatures. On worlds like Titan, methane exists as both a liquid and a gas, and scientists are investigating whether it could play a role in supporting life there. Methane-based life would have entirely different biochemistry from Earth-based organisms. Methane is much less reactive than water, which could present both challenges and opportunities for life. Life forms using methane as a solvent would have to evolve in ways that allow them to metabolize energy and build complex molecules without the use of water's polar properties. Methane life might rely on different chemistry, potentially using the carbon-hydrogen bonds in methane molecules to facilitate energy transfer and biosynthesis. The possibility of methane-based life is still largely theoretical, but the discovery of methane lakes on Titan raises the prospect of non-water-based life in a part of the solar system that was previously considered unlikely to support life. How could life evolve with alternative biochemistries? If life on other worlds evolved with alternative biochemistries, the very nature of life could look radically different from anything we can imagine. While carbon-based life uses DNA and RNA to store genetic information, life using silicon, ammonia, or methane might use entirely different molecular structures to replicate, store energy, and pass on information. Silicon-based life might have silicon-based analogs of DNA and proteins, using silicon-oxygen bonds to form complex molecular chains that can carry genetic information. Ammonia-based life might rely on ammonia-based nucleic acids, using ammonia to catalyze biochemical reactions in ways that water cannot. Methane-based life might use carbon-hydrogen bonds to create chemical structures that enable the storage and transfer of energy in environments too cold for water. These alternative biochemistries suggest that life could emerge in environments that are inaccessible to carbon-based organisms, such as frozen worlds, or those with extreme temperatures or pressure conditions. Life could evolve to use whatever materials are available to sustain it, making life in the universe much more diverse than we ever imagined. How do we search for life with alternative biochemistries? Detecting life that doesn't rely on carbon and water poses a significant challenge. We have designed our current instruments and methods to search for carbon-based life that exists in water-based environments, so we need to expand our search criteria. Traditional biosignatures, such as oxygen, methane, and carbon dioxide, are all based on the assumption of carbon-water life. For example, on Earth, we associate oxygen with photosynthesis, which is powered by solar energy and water. But alternative biochemistries might generate entirely different signatures. To search for life with alternative biochemistries, we must broaden the types of biosignatures we look for. Instead of focusing solely on water and carbon, scientists are exploring other chemicals and compounds that could indicate biological processes. For example, the detection of certain types of silicon-based compounds, ammonia, or methane might signal the presence of alien life. Additionally, future missions to moons like Titan or Enceladus may include instruments capable of analyzing atmospheres or ice-covered oceans for organic molecules that do not fit the carbon-water mold. The search for life beyond the familiar. As we continue to search for life beyond Earth, it is clear that we need to be open-minded and flexible in our assumptions. The universe may harbor forms of life that are radically different from the organisms we are familiar with, adapting to environments and chemistries we have yet to fully understand. Life may not depend on carbon and water as we think. It could evolve under entirely different principles, in ways that challenge everything we know about the nature of life itself. The discovery of life with an alternative biochemistry would not only reshape our understanding of the cosmos but also transform our perspective on what it means to be alive. If life exists in forms we cannot yet imagine, it would suggest that the universe is even more diverse and dynamic than we ever realized. As the scientific community continues to explore the possibility of life beyond Earth, the technology and missions designed to search for extraterrestrial life are advancing at an astonishing pace. From examining the icy oceans of moons like Europa and Enceladus, to sending probes to exoplanets hundreds of light-years away, humanity's ambition to find life in the universe is more than just an academic pursuit. It's a search for answers to some of the most profound questions about our existence. In this section, we will delve into the most promising missions and technologies being developed to search for life beyond Earth. We'll explore current and upcoming space exploration programs, the instruments being used to detect life, and the innovative ideas that might help us discover life forms, both familiar and alien, in the distant corners of the cosmos. The role of telescopes in searching for life. Space telescopes have revolutionized our understanding of the universe, and they are key tools in the search for extraterrestrial life. These powerful instruments help us detect exoplanets and analyze their atmospheres, a critical step in determining whether they might harbor life. Kepler Space Telescope. The Kepler Space Telescope, which operated from 2009 to 2018, was one of the most significant missions for discovering exoplanets. By continuously monitoring a section of the sky for small dips in the brightness of stars, Kepler was able to detect thousands of planets orbiting other stars. Many of these planets are in the habitable zone, where liquid water might exist, increasing the possibility that life could emerge. Kepler's discoveries have led to an explosion of knowledge about the diversity of planets in the universe. The telescope revealed that Earth-like planets are relatively common, and many of them are in the right conditions to support life. This has prompted scientists to expand their search for planets where life might exist, considering not just the traditional habitable zone, but also the extended regions where life could survive in more extreme environments. James Webb Space Telescope, JWST. The James Webb Space Telescope, JWST, launched in December 2021, is poised to take the search for life beyond Earth to the next level. With its ability to observe the infrared spectrum, JWST can detect and study the atmospheres of exoplanets with unparalleled precision. One of JWST's key goals is to examine planets in the habitable zone of stars that are similar to our Sun. JWST's powerful instruments will allow scientists to analyze the chemical composition of exoplanet atmospheres, looking for potential biosignatures, gases like oxygen, methane, carbon dioxide, and other compounds that might indicate biological processes. JWST will also be able to detect water vapor, a crucial component for life as we know it, and assess whether planets are capable of sustaining liquid water. What sets JWST apart is its ability to observe planets that are relatively close by but in the distant corners of the galaxy. Some of the planets it will study are super-Earths, which are larger than Earth but might have conditions conducive to life. These worlds are particularly intriguing because they could support a wider variety of environments, potentially even forms of life that differ drastically from Earth's organisms. JWST's observations are set to greatly enhance our understanding of exoplanet atmospheres and potentially reveal life in places we least expect. Nancy Grace Roman Space Telescope. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will provide complementary capabilities to JWST. Roman will specialize in wide-field imaging, allowing it to observe vast areas of the sky. One of its key missions is to search for exoplanets using gravitational microlensing, a technique where a planet passing in front of a distant star bends the star's light, revealing its presence. Roman's ability to survey many stars and discover exoplanets that may be difficult for other telescopes to detect makes it an important asset in the hunt for life. Its findings, along with data from JWST, will allow scientists to pinpoint exoplanets worth further study, particularly those with potentially habitable environments. Robotic space missions, probing for life on moons and planets. While telescopes provide an invaluable tool for studying distant exoplanets, robotic missions to planets and moons in our own solar system are equally crucial. These missions provide us with direct access to potential signs of life by analyzing the surfaces, atmospheres, and subsurface of worlds where life might exist. Mars missions, Perseverance and Curiosity. Mars has long been a prime candidate for the search for past or present life. Evidence suggests that Mars was once much warmer and wetter, with rivers, lakes, and possibly even oceans. Today, the red planet is cold and dry, but it still holds clues about its ancient history. NASA's Perseverance rover, which landed on Mars in February 2021, is currently exploring the Jezero crater, a site believed to have once hosted a lake. Perseverance's key mission is to collect samples from Mars' surface, which will eventually be returned to Earth for analysis. These samples could contain signs of ancient life, fossils, organic molecules, or other biosignatures, if life ever existed on Mars. The rover is also testing new technologies, such as the MOXIE experiment, which is producing oxygen from Mars' carbon dioxide-rich atmosphere, a potential stepping stone for future human exploration. In addition, the Curiosity rover, which landed on Mars in 2012, continues to explore the planet's Gale crater. Curiosity has already provided important data about Mars' ancient environment, confirming that water once flowed freely on the planet's surface. Both rovers contribute to the search for microbial life on Mars, past or present. Europa Clipper, a mission to Jupiter's ice moon. Jupiter's moon Europa is another key target for the search for life. Beneath its icy surface, scientists believe there could be a vast ocean of liquid water, kept warm by tidal heating caused by Europa's gravitational interaction with Jupiter. This subsurface ocean might be capable of supporting life, protected from the harsh radiation of space by the thick ice shell. NASA's Europa Clipper mission, scheduled to launch in the 2020s, will investigate Europa's ocean and ice shell. The spacecraft will conduct flybys of the Moon, using advanced instruments to measure the composition of Europa's surface and the potential habitability of its subsurface ocean. By analyzing the Moon's plumes of water vapor, ejected from the surface through cracks in the ice, Europa Clipper may find signs of life or the ingredients needed for life. Europa is one of the most exciting places in our solar system for the search for extraterrestrial life, and this mission will provide valuable insights into the potential for life beneath the ice. Enceladus, a moon with hidden oceans. Like Europa, Enceladus, a moon of Saturn, has a subsurface ocean beneath its icy crust. Enceladus has been studied extensively by the Cassini spacecraft, which found that plumes of water vapor erupt from the moon's south pole. These plumes contain organic molecules, which suggests that Enceladus might be capable of supporting life in its ocean. Future missions could send landers or rovers to Enceladus to collect samples from the plumes and analyze them for signs of life. Like Europa, Enceladus is an ideal target for the study of extremophiles, organisms that might be adapted to survive in cold, dark, and isolated environments. Technologies for detecting alien life. The search for life doesn't rely solely on sending missions to distant planets and moons. Advances in technology are helping scientists detect signs of life without physically visiting distant worlds. Here are some of the cutting-edge technologies that are being developed to detect alien life. Biosignatures and atmospheric analysis. As mentioned earlier, the search for biosignatures, chemical signs of life, is a central part of the quest to discover life beyond Earth. Advanced spectrometers and mass spectrometers can be used to analyze the composition of exoplanet atmospheres, looking for gases like oxygen, methane, and carbon dioxide. These compounds, when found together, are often associated with biological processes on Earth. In situ analysis. For missions that land on other worlds, instruments like drill probes and sample analyzers can be used to collect and analyze soil, ice, and rock samples. The Curiosity and Perseverance rovers on Mars are prime examples of how in situ analysis, conducting experiments directly on the surface of another planet, can yield important insights into potential microbial life. Artificial intelligence in astrobiology. As the volume of data from space missions grows, artificial intelligence, AI, is playing an increasingly important role in analyzing and interpreting that data. AI algorithms can help scientists identify patterns and anomalies in large datasets, speeding up the discovery process. In the future, AI may help detect signs of life by sifting through vast amounts of data from telescopes, space probes, and landers, enabling faster and more efficient analysis of biosignatures and other indicators of life. The search for life beyond Earth is not just a scientific endeavor. It is a profound philosophical and cultural quest that touches on some of humanity's deepest questions about our place in the universe. If we were to discover definitive evidence of extraterrestrial life, it would challenge many of the assumptions and beliefs that shape our understanding of existence, consciousness, and the nature of life itself. In this section, we will explore the philosophical implications of discovering life beyond Earth, the potential societal impact on our worldview, and how the knowledge of alien life could change our ideas about religion, ethics, and our relationship with the cosmos. The cosmic perspective, our place in the universe. For centuries, humanity has viewed itself as the pinnacle of life in the universe. Earth, in our collective consciousness, has been seen as a rare and special place where life, in all its complexity, flourishes. The Copernican revolution, which dethroned Earth from the center of the universe, was the first major shift in our understanding of our place in the cosmos. But the possibility of discovering extraterrestrial life represents an even more profound shift. one that could dramatically alter our perception of human significance in the vastness of space. The discovery of even simple microbial life on another planet or moon would suggest that life is not an earthbound anomaly but rather a cosmic phenomenon, something that may occur across the universe. This idea would challenge humanity's belief in its exceptionalism and open up the possibility that life exists in forms we cannot yet imagine. It would imply that life is a common outcome of the right set of physical and chemical conditions, making Earth not the center of the universe but one of many habitable worlds. In the grand scheme of the cosmos, Earth might not be as unique as we thought. This realization could lead to a humbling of humanity's ego, reminding us that we are just one species on one small planet in a vast and ancient universe. It would prompt us to think about life in a more cosmic sense, where Earth is not the only cradle of life and humanity is not the only intelligent species. However, discovering alien life could also inspire a sense of awe and wonder, urging us to consider that life elsewhere might have evolved in entirely different ways. What might such life look like? Could it possess intelligence, consciousness, or even a form of culture we cannot fathom? These questions would drive an entirely new chapter in human curiosity and exploration. Theological and religious implications. A new creation story? The discovery of life beyond Earth would undoubtedly have profound implications for religion and theology. For many religious traditions, the existence of life on Earth is viewed as part of a divine creation, and humanity is often seen as a special creation with a unique relationship to the Creator. The idea of extraterrestrial life challenges these theological concepts and raises important questions about the nature of creation and divinity. For example, some religious interpretations of Christianity, Judaism, and Islam assert that humanity is created in the image of God, and that Earth is the center of divine attention. If life exists elsewhere in the universe, these belief systems might have to reassess their view of human uniqueness. Would the discovery of alien life diminish the specialness of human beings in the eyes of God? Or would it expand the understanding of divine creation to include life across the universe? In other faiths, such as Hinduism or Buddhism, the idea of extraterrestrial life might be more easily integrated into existing beliefs. These traditions often view the universe as interconnected, with many different forms of life existing in a cyclical process of birth, death, and rebirth. The discovery of alien life could be seen as an affirmation of the diversity and interconnectedness of existence. Ultimately, the discovery of alien life would challenge many of our theological assumptions and require religious traditions to engage with questions about creation, consciousness, and the purpose of life. For some, the discovery might be seen as evidence of a greater divine plan. For others, it might provoke theological rethinking and reinterpretation of ancient scriptures. Ethical considerations. Our responsibility in the cosmos. As humanity ventures further into the cosmos and potentially encounters alien life, we must confront a range of ethical questions that will shape our actions. If we find life elsewhere, how should we treat it? Should we attempt to communicate with alien species? Or should we proceed with caution to avoid potentially disrupting delicate ecosystems? What responsibilities do we have as we explore and perhaps colonize other worlds? One of the most pressing ethical concerns revolves around the potential impact of human exploration on extraterrestrial life. In some ways, our historical record of exploration on Earth offers both lessons and warnings. The arrival of humans in the Americas, Australia, and other regions led to the displacement and destruction of indigenous populations and ecosystems. If we encounter intelligent extraterrestrial species, the consequences of our actions could be profound, and we must ask ourselves whether we have a responsibility to preserve alien ecosystems or to interact with extraterrestrial beings in a respectful and non-exploitative way. This raises another question. Should humanity colonize other planets or moons if they harbor alien life? As we expand into space, should we leave places like Europa, Enceladus, or Mars untouched, in case they harbor microbes or ecosystems that could be destroyed by human activity? Many scientists advocate for a planetary protection policy to prevent contamination of other worlds, ensuring that we do not harm alien life or introduce Earth microbes that might disrupt the natural balance of these environments. The search for intelligent life, the Fermi paradox. One of the most intriguing aspects of the search for extraterrestrial life is the possibility of discovering intelligent alien civilizations. Given the vast number of stars and planets in the universe, it seems statistically likely that advanced civilizations could exist somewhere. However, despite decades of searching, we have yet to find any conclusive evidence of intelligent alien life. This paradox is known as the Fermi paradox. If the universe is so vast and old, why haven't we found evidence of intelligent extraterrestrial civilizations? Several possible explanations for the Fermi paradox have been proposed, each of which carries its own philosophical and societal implications. Rare Earth hypothesis. Perhaps intelligent life is incredibly rare, and Earth is one of the few places where it has arisen. This could be due to a unique combination of conditions, from the right star to the right geological history. If this is true, the discovery of extraterrestrial life might make Earth even more special, rather than less. The Great Filter. Another possibility is that a great filter exists that prevents civilizations from reaching an advanced technological stage. This filter could be an event in a species' evolutionary history that is unlikely to be overcome, such as the development of intelligence or the ability to prevent self-destruction. If this theory is correct, discovering alien life might indicate that other civilizations have been wiped out, raising questions about the future of humanity's own survival. We are not looking right. Another explanation suggests that we might not be searching for life in the right way. Perhaps alien civilizations are using technology or communication methods that are beyond our current understanding, or they are so distant that we are not yet able to detect them. Zoo hypothesis. Some have proposed the idea that advanced civilizations are aware of us but are deliberately avoiding contact, either to preserve their own safety or because they believe it is unethical to interfere with our development. In this scenario, Earth might be akin to a zoo, where alien civilizations observe us without intervening. The Fermi paradox touches on the profound question of whether humanity is truly alone in the universe, and what it would mean for our future if we were to encounter other intelligent life forms. The discovery of such civilizations would be a momentous event, raising questions about the potential for interspecies communication, cooperation, or conflict. The future of humanity. What happens after we find alien life? The discovery of extraterrestrial life would forever change the trajectory of human history. It could foster new technological advances, new scientific pursuits, and a renewed sense of wonder about the universe. It could also provoke existential questions about the future of humanity. How do we navigate the vast cosmic ocean, knowing we are not the only intelligent species? How should we prepare for the potential challenges and opportunities that might arise from such a discovery? The implications of finding extraterrestrial life are as vast as the universe itself. It could lead to a deeper understanding of our place in the cosmos, challenge our assumptions about intelligence, and inspire us to reach beyond the stars. As humanity's search for extraterrestrial life expands, so too do our imaginations about the possibilities of life's existence beyond not just Earth, but the very universe we know. One of the most profound and mind-bending ideas in modern cosmology is the multiverse theory, the hypothesis that our universe is just one of many, each with its own set of physical laws, constants, and possibly even forms of life. This section will delve into the multiverse and its philosophical, scientific, and speculative implications for the existence of life beyond Earth. Could life exist in parallel universes with entirely different rules of existence? If so, what would that mean for our understanding of life, consciousness, and reality? The basics of the multiverse theory. The multiverse theory suggests that our universe is not the only one. In fact, there may be infinitely many universes, each existing separately with different sets of physical laws and constants. These universes may vary in size, shape, and nature, and while some may be similar to ours, others could be radically different. There are several different interpretations of the multiverse theory, each of which offers a unique perspective on the existence of life beyond Earth. The many worlds interpretation, MWI, this is a quantum mechanical interpretation that suggests every decision or possibility in the universe splits reality into multiple, parallel timelines. For example, every time a decision is made, an alternate universe is created where the opposite choice occurs. This theory proposes a potentially infinite number of universes, each with slight or major variations from our own. Could intelligent life exist in other versions of the universe, where different events and decisions led to the rise of different civilizations? Bubble universes, eternal inflation. According to the theory of eternal inflation, the universe is constantly inflating, with regions of spacetime growing at different rates. These bubbles of spacetime could each contain a universe with its own laws of physics. While our universe has developed with the specific conditions that allow for life as we know it, other universes may have entirely different physical constants, leading to potentially wildly different forms of life if life exists at all. String theory and the landscape multiverse. String theory, which aims to explain all particles and forces in the universe as tiny vibrating strings, suggests that the fundamental properties of the universe might not be set. Instead, they could vary from one universe to another. This leads to the concept of a landscape multiverse, where an infinite number of universes each have different physical laws, dimensional structures, and fundamental constants. Mathematical universes. One of the more radical ideas is that the universe is not just a collection of particles but a mathematical structure. In this view, universes with different mathematical properties could exist. Some physicists argue that any self-consistent mathematical structure can correspond to a universe, including ones where the concept of life might be based on completely different principles than what we understand. The possibility of life in the multiverse. If the multiverse exists, the implications for life become mind-boggling. Could life exist in other universes, governed by entirely different rules of physics? In some models, universes might have different fundamental forces, such as gravity being much stronger or weaker, or even entirely new forces that we don't experience in our own universe. Different physical laws, different life forms. In a universe where the laws of physics are not the same as ours, the very definition of life could change. Life as we know it is based on carbon chemistry, with water as a solvent and the need for stable environmental conditions. However, in other universes with different physical constants, life could be based on entirely different chemical processes. For example, instead of water, other solvents could be used: ammonia, methane, or even liquid hydrogen. Life in such environments would likely be unrecognizable to us, with forms of intelligence and consciousness that might not rely on carbon at all. This could lead to entirely new conceptions of biology, intelligence, and even consciousness, challenging our very understanding of what it means to be alive. If the laws of physics were altered slightly, other universes might host life forms with radically different morphologies or sensory capabilities. Imagine life that does not experience time as we do, or beings who perceive the world through an entirely different set of senses. Perhaps beings that can see, sound, or communicate using non-physical means, such as telepathy. Parallel Earths and alternative histories. In some multiverse scenarios, there could be universes where the history of Earth took a different course. These parallel universes could contain versions of Earth where life evolved differently due to slight changes in environmental or biological conditions. For example, in one universe, dinosaurs might never have gone extinct, and intelligent life could have evolved from them. In another, early humans might have made different decisions during key historical events, leading to an entirely different civilization. While these alternate Earths might resemble our own in many ways, the subtle differences in their histories could create life forms with experiences, technologies, and societies quite different from what we know. These worlds might hold the answers to some of our most persistent questions, such as what our own future might look like, Or what might have happened if certain historical events had unfolded differently? The ethics of life in a multiverse. If the multiverse is real, it raises profound ethical questions about how we perceive life in different realities. Would we treat life in alternate universes with the same respect and consideration we give to life here on Earth? Would we interact with these universes, and if so, under what conditions? The very nature of consciousness in a multiversal context would also challenge our understanding of ethical responsibility. If life exists in different forms across the multiverse, should we try to contact or interact with these forms of life, or should we respect their autonomy, just as we might wish to preserve Earth's ecosystems and indigenous species? The potential for encountering sentient life in a multiverse scenario could also challenge human concepts of rights and personhood. As we grapple with these ethical questions, it becomes clear that the discovery of life in a multiverse would push humanity to reconsider its role in a vast and interconnected reality. It would raise fundamental questions about the nature of existence, intelligence, and our shared moral responsibilities across multiple dimensions. The search for multiversal life, a new frontier. While the idea of life in parallel universes or alternative dimensions might seem more like science fiction than science, many modern theories in physics suggest that such possibilities might not be as far-fetched as they seem. The multiverse theory remains speculative, and it might be years or centuries before any concrete evidence is found to support it. However, the search for life in a multiversal context is already beginning to take shape in the form of advanced theoretical models in physics and cosmology. For example, some physicists are exploring the idea of detecting echoes of other universes through gravitational waves, ripples in space-time that might provide evidence of interactions between universes. Others are looking at the quantum mechanical properties of particles to understand whether multiple universes could interact in ways that might make life in them detectable. As our technology and understanding of physics progress, it's possible that the multiverse will move from the realm of theory into something that can be explored and tested. The final frontier, the nature of life itself. The discovery of extraterrestrial life, whether in our universe or across a multiversal expanse, would profoundly change our understanding of life itself. If life can exist in multiple forms and across multiple realities, we would need to expand our philosophical and scientific definitions of life, intelligence, and consciousness. Are the principles that allow life to emerge in one universe applicable across all universes, or is each form of life unique to its environment? Does the existence of life in one universe suggest that the very laws of physics might be a universal blueprint for all life, or do we need to rethink our assumptions about the nature of reality itself? These questions will not only shape our understanding of life, but will also guide humanity's future exploration of the cosmos, whether within our own universe or beyond, into the realms of the multiverse. The search for life beyond Earth is not just a quest to discover other beings. It is a journey to understand the universe itself and the very nature of existence.